Okay, let's dive right into this. Welcome to today's explainer. We're going to go ahead and skip the dry introductions and jump straight into the hidden, honestly kind of dramatic electrical battle that happens every time you power up heavy machinery. Literally, every time you flip a switch, this high-stakes clash of physics takes place in mere fractions of a second. So today, we are totally decoding the dynamics of electrical inrush and starting currents.
Now, to hook right into why this actually matters to us, let's look at something you've probably experienced firsthand. You turn on a heavy machine, right? Maybe it's a massive AC unit, an industrial saw, or honestly, even just a really heavy-duty vacuum cleaner. And for a split second, the lights in the room dim and flicker. We've all seen it. But why does that happen? Well, that visual flicker is an everyday physical symptom of a massive, temporary demand for power just pulling down your local distribution grid. It's a common nuisance, sure, but it's driven by some intense theoretical physics that engineers absolutely have to manage.
To really see what's going on here, we kind of need to dilate time. When you hit that power switch at 0 milliseconds, what feels like an instantaneous start to you and me is actually this complex multi-stage electrical event. In just the first half cycle of alternating current, we're talking literal milliseconds here, there's an inrush peak where the current spikes to a massive 10 to 20 times the normal full load current, or FLC. Then, over the next several seconds, the machine draws a starting current. This is still highly elevated, sitting at 4 to 8 times the normal load, before it finally settles down into a steady hum.
So here's the absolute crucial takeaway of this explainer. We've got to clarify a major misconception. The terms inrush current and starting current get thrown around interchangeably all the time by lay people and actually sometimes even by technicians who should know better. But as we just saw in that timeline, they are entirely different phases of the startup process. They are governed by completely different physical principles, and they cause completely different types of headaches for an electrical system.
Let's break down the data to see exactly how different they are. First up, inrush current. Its duration is incredibly short, like just a fraction of a cycle. Its magnitude is a massive spike, 10 to 20 times normal operating current. Why? Because it's desperately trying to magnetize the core or charge up capacitors. And its main focus for trouble? It causes those instantaneous, super annoying nuisance trips of your circuit breakers. Now, compare that to starting current. Its duration is a lot longer, lasting several seconds. The magnitude is lower than inrush, but still a really hefty 4 to 8 times normal current. It's caused by overcoming physical inertia. And the main threat here? Thermal heat. It causes overheating over those crucial few seconds.
All right, Section 1, the physics behind the surge, why it happens. Let's get into the invisible mechanics of it all.
First up is this concept called lack of back electromotive force, or back EMF. Think of it like this. When an electric motor is spinning, it acts a bit like a generator in reverse. It creates a force that pushes back against the incoming electricity, which naturally limits the current being drawn. It's a nice equilibrium. But at the exact moment of startup, when the motor is at 0 speed, it generates absolutely zero back EMF to oppose the supply voltage. There's no pushback. It's basically just a wide open door for electricity to rush right in.
Now, what's really interesting about this slide is the mechanical side of the equation. A heavy metal rotor sitting completely still has an immense amount of inertia. Think about the effort it takes you to push a stalled heavy car. Getting it rolling takes literally everything you've got. But once it's rolling, it's pretty easy. Well, a stationary rotor demands an enormous surge of electrical power from the stator just to create that initial torque to break the standstill.
Okay, so those last two concepts perfectly explain the starting current that lasts for several seconds. But let's shift back to the very first few milliseconds, the true inrush current. What causes that massive 10 to 20 times spike? Well, it's largely due to magnetic saturation. When a transformer or a motor is first powered on, its magnetic iron core can get almost completely saturated with magnetic flux in just the very first half cycle of alternating current. For a split second, its electrical resistance basically vanishes, and that leads to a blindingly fast, absolutely massive current surge.
And hey, it's vital to point out that this isn't just about giant industrial motors. Even small, everyday electronics experience inrush. Why? Well, because the circuits inside your TV or your laptop charger contain empty capacitors. When you first plug them in, those completely uncharged capacitors behave exactly like tiny short circuits. They greedily gulp down as much electricity as they physically can for a fraction of a second until they're fully charged up.
Moving on to Section 2, when surges cause damage, the high stakes, because leaving this unmanaged has real physical consequences.
We really need to treat this list like a rap sheet of destruction. First up, voltage dips, or brownouts. This is the flickering lights we talked about earlier.
The sudden draw literally sags the local distribution grid. Second, nuisance tripping. Your circuit breakers mistake that massive instantaneous inrush for a dangerous short circuit and just shut the whole operation down. Third is thermal overload. Drawing 4 to 8 times normal current for several seconds generates incredible heat. I mean heat that can literally melt the winding insulation inside a motor, destroying it permanently. And finally, mechanical stress. The magnetic forces during startup are so incredibly violent they can shear bearings or literally snap a solid metal motor shaft right in half. No way you want to deal with that.
Which brings us to Section 3, Taming the Electrical Surge, soft starting. Let's look at the ingenious workarounds designed to save our grids and machines. Let's walk through a classic step-by-step mechanical workaround, the star-delta starter. Normally, when a motor starts up in its standard delta wiring configuration, it pulls maximum current. But engineers figured out a clever trick. If they wire the motor to start in a star configuration, it artificially chokes the voltage. It limits that starting current to exactly 33% of its normal direct online current. So it tames the beast, gets that heavy rotor spinning slowly and safely, and then, once it's up to speed, physical contactors literally click over, switching the wiring back to delta to unleash full power. Pretty brilliant, right?
But of course, modern engineering relies heavily on solid-state digital solutions. Dedicated soft starters use components called silicon-controlled rectifiers. These guys gradually electronically ramp up the voltage. This allows them to take that terrifying 6 to 8 times starting current and dramatically drop it down to a highly manageable, incredibly safe 1.5 to 3 times the full load current. It's a real game changer that protects the machine and the grid simultaneously.
And this brilliantly illustrates the variety of tools engineers have at their disposal today. We've got variable frequency drives, or VFDs, which control the actual frequency of the AC power to start a motor with almost zero current increase. In electronics, we use NTC thermistors. These are clever little resistors that have super high resistance when they're cold, which totally blocks the inrush spike. But as the current heats them up over a few seconds, their resistance drops to zero, letting normal current flow. We've also got auto transformer starters that step down voltage, or honestly, simply procedural solutions like staggered starting, just ensuring a factory doesn't turn on 10 giant machines at the exact same millisecond.
Bringing our narrative full circle, we arrive back at our core premise. As this quote perfectly notes, while the terms are casually swapped around, inrush current and starting current represent different phases of the startup process. Mastering this aspect of electrical engineering means deeply respecting both phenomena. You absolutely must mitigate the lightning-fast, millisecond magnetic burst of the inrush, while simultaneously managing the multi-second mechanical heat and acceleration of the starting current.
So, the next time you turn on a heavy appliance and see those lights dim for just a fraction of a second, you'll know exactly what's happening. You are witnessing inertia, magnetic saturation, and thermal limits fighting it out in real time. And it leaves us with a fascinating final thought to ponder. What other invisible forces are battling it out behind the scenes in the machinery of our daily lives every single time we carelessly flip a switch?